Hi there. Yeah, this is Nicolai Josuttis, and I'm live from Germany here. And we have to talk about Move Semantic. I want to tell you about the hidden secrets I found. And in the next 1 hour, I will talk about just how we can move better in C++. Move Semantic was introduced in C++ 11. And it's time to talk about a little bit about the hidden features of Move Semantics. So let's start. The whole session will be just that we program a little bit. So this is my class. I want to program with you. This is a class cont for container, internally using a vector of string. And yeah, with the default constructor, so we can create the container, and of course we can insert some elements. Maybe we create a string, print out a string before we insert it, and then we print it out. And then let's print the whole content of the container, which in this case is only hello. So let's start with a few basics before we go into detail of Move Semantics. So first of all, for the rest of this talk, I will skip the qualification of SCD, except for move and forward, to make clear that we use here key elements of Move Semantics. And then I will use pretty short strings, which usually don't benefit from move. So let me please tell you that we assume we have no small string optimization, or that these strings have significant size. So when we move to somewhere, the whole string is, the memory is moved or copied, depending on whether we have a move or copy. And then I have a helper function where I can print out the memory this string internally uses. So you see it here, we print out where this string str was allocated, the internal memory of the string, so the string data. So, and what we can see here at the beginning is now when we insert a string as it is without qualifying it with move, we see that the string gets copied. We have a different address when the string is inside the container. And yeah, so we copy. Good. And the whole idea of Move Semantic is that we avoid these copies because copying is expensive. So we avoid these copies when we can and when we should and when we would like to do that. So let's now come up with a new function returning a string by value and use it. And as you see, if you directly use this string to insert it into the container, it gets copied again. Why that? Because in our class, we have no support for Move Semantics yet. And yeah, so we have a copy. So how can we improve that? Well, the usual way, as a vector class, for example, does it, we overload the inserters to have some support for Move Semantics. And that means we have a new function insert, taking an R-value reference. We take the value here, the temporary value that comes here. We get the compiler automatically calls this insert function because the compiler knows that this object is about to die. It's a so-called PR value. And this value is moved then internally inside the container. Now you might wonder, why the hell, if this object has Move Semantics as a temporary object, why do I have to qualify the move here? And the question, the answer is, if the caller of a function says, I no longer need this value, the receiver of this value still has to say, when this code no longer needs the value, you might use it multiple times. And so in this case, the last time we use it, we need it, which is the only time here, we here move then this value into the container. And as you see now the address of the memory, internal memory of the string is moved into the container. So we have move semantics implemented here. So far, so good. If you're familiar a little bit with move semantics, that might be nothing new for you. So the only benefit from this is, assume we have here the beginning where we copy the string. We have a name for the string and we insert it. And here we directly use a return value. It's a good idea if you use move semantics to avoid objects with names. Okay, a few things here. First of all, look at the top of this function. This function returns a string, so an std string here. If we come up to return a const string, then move semantics will be broken. You see that here. We have here copying now, and you see that in the internal data, the address we had for this string when we got it returned from getString is now internally we have a different memory. And it's clear because we pass a constant string to move semantics, and this constant string here in insert is not allowed to be modified. The usual way to implement move semantics is to steal some value, but that is only possible for an R value reference for a string that is not const. So in this case, here, not this implementation will be called. This insert will call the normal insert for const strings where we still need the value. So move semantic is disabled with const. And by the way, that means if you have functions and if you have learned for some reason in the past that when you return by value, you might better qualify this by const, please don't do that anymore because you are, as you see, hindering move semantics. Yeah, that means your program runs unnecessarily long. So don't do that anymore. Okay. So you might see, okay, here in my implementation, I take a string and I move it then in the internal vector here of this class. So let's see how we, does it mean that we as a programmer also sometimes need move? Because you don't see a move here. However, you can't avoid using move. And from time to time, I hear people saying that try to avoid move, but it's easier said than done. Let's see for some examples where we need a move. For example, here, if your object has a name, so if it's a parameter, for example, you need move to move it to somewhere. But this is not the only case. If you need it twice, like here, let's do something. Let's print the value out with its memory, and then let's move it in. If you need an object twice, you need a name for it, whether the name is the value or a reference, doesn't matter. But if you need the same object twice, you can't do that without, or with, yeah, normally without any big effort. And in this case, that means now we qualify str here with move to say we no longer need this value. And so we have a couple of reasons as a programmer to use move even as an application programmer. So you need it for parameters. So if you have a parameter, you no longer need the value move. But you need it also for arguments. So the other side, the calling side of a function. So a famous example is getLine. Let's read from a stream a new string into str here. That's an out parameter, which of course also has a name. And if you return values or just values used multiple times, as you see here, and last not least, sometimes it's more readable to have names for objects. And the most important thing still is that we have readable and maintainable code. So let's, so there are a couple of reasons to use move. So move is something you should know, you should understand. And please note that after this move, the string you are still able to use. Move means I no longer need this value here. Almost every word counts here. I no longer need the value of str here. You do not partially destroy str. Str will still be there. It will just have some value. It will be valid and will just have some value. Okay, and again, note that cons will have the effect that you no longer move. So here you see the whole program. If the return value from getSur is assigned to a const string and we call move, then we will have a different value in the container because the copying insert function is used. You might wonder why we don't think this is an error. If I have a const, so move has no effect, why shouldn't I have an error here? Well, think about generic code where we have templates. You might get this str of a type T. So this type T might or might not be const, and your generic code should work in both cases. So in that case, if it's not const, the move would have an effect. And if it is const, the move will just be ignored. And the fallback mechanism of move semantics will be used. And that means we fall back to copy semantics, which is implemented here. However, there's something which not everybody knows in C++. It's possible to overload for const moved values or const values that are marked with move, I should say. So here it is. This is an insert. Insert takes a const string R value reference. This is technically possible in C++. The only problem is we have no real semantic meaning for that, because usually the contract of move semantics means for the caller, I no longer need the value. And for those who implement against that, okay, I can steal the value, but I have to ensure that there is still at the end a valid string here so that the caller can still use the string without knowing its value. So if you say, I no longer need the value, but you are not allowed to modify the string, that's a semantic contradiction. So it makes no real sense. It's possible to do that, and I bet we will have a usage for that, a useful usage for that in C++ as with everything. But in general, it makes no sense to implement functions like this. I think we have almost no place in C++ where we use that, just in some wrapper types where we wrap behavior, just in case somebody has special behavior for that. We don't want to change the behavior. We have overloads for const R value references. Look at class optional, for example. It has overloads for const R value references. Okay, so far so good. That's it. That's the basics of this class. And of course, we should finally make it generic. And that means I would take the class and say, okay, this class is parameterized for a template parameter T. So we have internally a vector of T's, and we are inserting a const T reference or a T R value reference. So this is an L value reference. So this is the insert when we still need the value. The caller still needs the value. This is a function is called when the caller no longer needs the value. So here's a question, by the way, in the talk. The question is why I'm using pushback and not mplaceback. Well, can we use mplaceback? Yes, of course you can use mplaceback here. It's also possible, and it works. Mplaceback has all support for move semantics, and please note that usually the implementations of pushback just call mplaceback for this whole argument. So therefore, it's always possible. We still recommend to use pushback if you have already an object of the right type or expect an object of the right type. while using mPlaceBack if you have something that is used to create the object on the fly or in the vector. So, but yes, you can use mPlaceBack here. Okay, so, and as we have a container now, let's use a container of bool, and that's also possible. So we have here a type bool, which has no special support for move semantics. It's just a fundamental data type, but it works. Move for bool does not have any effect. We can insert false, we can insert true, and we can print that out, and you see that the output works here. Okay, so to some extent, that's the basics, and that was what is usually taught in trainings that talk about C++ or move semantics or modern C++ or whatsoever. So now let's look at some more interesting stuff. So first of all, here, look at this side. We have an overload for two insert functions. So one for const L value reference, one for non-const R value reference. In principle, you can have two others. You can have one for non-const L value reference. Semantic meaning would be I have an output parameter or an in-out parameter. Here the semantic meaning is I have an in parameter, and here the semantic meaning is I have something you can steal, so to adopt from me as a caller. And we have seen they have this a little bit esoteric case of const t double ampersand, so R value reference for a const t. So that's between 2 and 4 overloads. And if you pass multiple arguments and you want to support our cases perfectly, then you need all combinations of these overloads. So between 4 and 16 overloads you need then. And for 3 arguments, you would then need 8 or 3, 9, 20, 27 overloads, something like that. And that's, of course, something we don't want to do at the end. So can we somehow combine this insert function into one function? And there are 2 answers. The first answer is yes, you can simply insert the value by taking it by value and move. And surprisingly, for types that have not where moving is not expensive, this is not worse. I've done some measurements with the strings, and you only add some more moves, which are cheap for strings, but it works the following way. Whenever we push back a new value into the vector, we anyway have to create a new object, a new element, in this case of the vector. So all we do is we create it earlier here. Whatever we get it by value. And as an only exception, if somebody is giving me a temporary object or an object marked with move, if we pass by value, this is move initialized, or this v is moved initialized with that value. So whatever we get, we either create here an object, or if we got a movable object, we create here our v, and then we move it into the vector. So the number of memory allocations for strings are the same. The number of moves grow up. And you can always do that if you have to, if you really in all cases have to adopt things, adopt values. So you anyway have to create your own copy or store your own copy of the value. A typical example are constructors. Your constructor can take an argument by value and move it into the member if you have a string member or so. However, be careful with that. It's not always a good strategy. It works sometimes. So Move Semantics makes a call by value and return by value cheap, as long as what you return or what you pass is an R value, which is an object you no longer need, a temporary object, or an object marked with move. So yes, you can take by value and move, And you can use that, for example, to initialize string members in a constructor. However, let's look at another example. Don't do that all the time. Don't do that, for example, when moves are expensive, or in this case here, insert if. If I take a value and I don't know whether I need this value, so I have here an if condition, and to some extent I will push back, well, here between the dot dot dots, there's a v, dot dot dots I use here because we might need a move or not here. So whatever we want to do here, if it's conditional whether we need the object or not, then this is not a good strategy. For temporary objects, it's still okay, because anyway, we move the temporary object here as to v, and then we might or might not use it and move it into the vector. But if you have an object that is not movable, so like an L value, so an object with a name, then it could be expensive. We would copy the object, although we might not move it into the vector. So what could we do instead? Well, we could, well, first of all, I should say, don't take by value and move if you set an existing value. You have already memory for this value, so setters should not use this technique. Inserters could, but conditional inserters should not. You might not, like here, you might not adopt the value. And if move is expensive, so if your object has 1,000 and an STD area of 1,000 doubles, that could be a problem, at least from performance point of view. So what can you do then instead? And the usual way you use that is use perfect forwarding. So perfect forwarding, most of you probably have heard that. The audience in CppCon is usually some expert, has some level, but let me just bring up the usual three rules of three things you need to have a universal reference. A universal reference is something where you say, let's take the parameter and as it is, forward it somewhere else. And so there are three things you need. You need a template parameter, an R-value reference argument, and std forward. So here's a way to do that. This looks like we are hitting the point. So that's a template parameter, 2 ampersands here. And then we use pushback. And as you might have learned already, this pushback should be a conditional move. So it should only move if we have here what we pass is movable. And the interesting thing is, to this R-value reference, you can't pass everything you want. Oh, there's a bug in this slide. This U should be a T, of course. And okay. So first of all, a couple of things to clarify here. First of all, I use the term universal reference. You might think, what the hell is he talking about? Because there are two terms for what we talk about here. There's another term, it's called forwarding reference. It's a nightmare and a mess we have in the C++ community here. We have introduced the term, well, Scott Myers introduced this term in 2012, right after C++ 11 was published, and he used universal reference, and you can still use this term in a couple of books and still find it in a couple of chats, and some people like me are using it still. And then the C++ Standards Committee decided in 2014, after C++ 14 was out, that they want to change this name to forwarding reference. Actually, they didn't have any name at all. Universal reference was not part of the C++ standard. So they introduced the term forwarding reference, which is then formally the term for this in C++ 17. This is, well, we have enough problems with C++ with all the rules. Now, intentionally introducing two different terms just to confuse the audience and the people in the community even more, I think is a nightmare in itself. But as we can see, we still have the books of Scott Myers, and we still saw books about universal reference, and forwarding reference is used. Even worse, universal reference is probably the better term. I will tell you about that in a moment. So, we have it seems we have a universal reference, a forwarding reference, template parameter, argument with 2%, forward with ft forward. So we should perfectly forward the argument if it has move semantics, otherwise we should not. So this is what we have here. It works fine for a temporary object. So if we pass here a temporary object, it works fine. But if we try to insert an object that's not marked with move, so an object with name, so what we call an L value, this will not compile. What is the problem? Well, the rule of thumb I just showed you was not precise enough. This is not a universal reference, or this is not a forwarding reference. There are additional constraints, and you have to be very careful to find out what is a universal reference and what is not. So here's one condition. If t, it's not enough that t is a template parameter. This t must be a template parameter of this function. So here we have a template parameter here on top, which belongs to the class. So that does not make this a universal reference. This function does not fall under the rules of function templates. It's what we call a temploid. So it's some templified or generic code, but it's in the moment we know type T for the class, we have here find if as a normal member functions following the rules of ordinary member functions. So this is not a universal reference. Once we know T, we just accept only T with 2%, and P with 2% only accepts R values, so only accepts objects that are marked with move or temporary objects. There are a couple of other things that are not allowed or make this not a universal reference. So for example, if this argument V is in addition qualified with const or volatile, it's not a universal reference. And if this T is not a pure T, so not adjusts the type, the template parameter type, if you, for example, use T : value type, then it's also not a universal reference. And so you have to look very, very carefully when you see 2 ampersands in a declaration to understand what it is and what it is not. And it's probably the biggest mistake we made with move semantics, that we had no special syntax for universal or forwarding references. If we would have another syntax, some people sometimes say 3 ampersand, which make everybody laugh, but it would help. We would understand the rules, and there are different rules. In addition, we have problems that how we qualify a string as a universal reference, a concrete type. We need a requires clause or an enable if. So we have a couple of problems, a huge amount of problems with the fact that these 2 ampersands are used for 2 different things: ordinary R value references and universal or forwarding references. But that's the way it is now. And the way to solve that is pretty easy. Now you see why here's a U, that was a copy-paste error. We have to say that this is really a function template parameter. So let's declare here another template parameter U. And this parameter U, we now then forward this into the function. And now it's a universal reference. Now it works for L values for objects that have a name, and for R values for temporary objects, or for objects that are marked with move. Now, on the other hand, we now take all types, all parameter types. It's not so easy now to restrict this to type T, and we might use a requires clause or some enable if stuff to say, but this function should only be there if this U is the same as type T. And that's also a problem that we have the same syntax. there was a question here about any other syntax for forwarding references. Yeah, a lot of proposals might come now, so using a $sign or so. That would be a different discussion once we think about how to use things. In general, we are very careful to introduce new tokens, even new characters for tokens like the $sign. But of course, that would be possible, and that's a different discussion. We are backward compatible. We have now this behavior, and that's a problem we have. So where am I? Okay, so let's clarify a little bit more what you need. You need a function template parameter. You need an argument with t or whatever the parameter name is, and 2 ampersands, please no const, no volatile, and then you can forward, and then you have perfect forwarding. Please note that we have a feature called full specialization of function templates. This is now a function template inside a class template. And it's allowed to fully qualify this. Here is a qualification for type string. Now, the interesting question is this a universal reference or not? So you might say, oh, a type, that's a real type name, std string, ampersand, ampersand. That must be an R-value reference. That can't be a universal or forwarding reference. That's not true. If your template, if your function is a full specialization of an existing function that takes a universal reference, then this is also a universal reference. So even if you see std string ampersand ampersand, you have to look a little bit around to see whether this is maybe a universal reference. So yeah, again, we have the same syntax for both, and that's that's a problem. Okay, so we can use this feature like universal references for something like insert if, where we say now, let's pass multiple arguments. So instead of passing one argument, let's pass multiple arguments. And that will be that we use variadic templates. So variadic templates are used and in a way that you say, I have an arbitrary number of type names, and then I take an arbitrary number of arguments of these type names. And to have these arguments, for these arguments, perfect support for Move Semantics or also not for Move Semantics, so they take everything and they pass everything perfectly forward. We declare this with 2 ampersand as you learned for a template parameter, and then we forward it. And here's a way to forward it. I want for each and every element I pass here, push them into the vector. So I use a helper function push, which I call for each and every argument. And this is a feature of C++17 fold expressions. This is a comma-separated list so that for each argument we call push the forwarded argument. And here's another error. Oh my goodness, too many. Copy and paste. So this should be U, of course, here, and this should be V. So because that's the name of the type and that's the name of the argument. Last minute changes even after I compiled things. I shouldn't do that. Good. So where do we find push? Let's call for whatever we got the function that inserts this into the vector. Well, let's use a lambda. Lambdas can also have universal references. Then the parameter is auto-ref-ref. Auto-ref-ref is another way to define a universal reference, taking everything, and then we can use perfect forwarding. How do we use perfect forwarding here? Well, we take, again, forward for this x, but we need the type of the x, the decal type of x, and then we pass the x and we push it into the vector. So yeah, that's already a little bit tricky, this code. And a lot of features and modern C++ features are used here. But you see here at the end, we have an arbitrary number of arguments we take. We forward perfectly for each argument with push to here this push function. And this if the condition is correct, we push it then back perfectly in the vector. So that's the way you can implement that. So, universal reference. Now let's go to one level further, because we have a few other problems we can use or we might be surprised about. So one thing is auto ampersand ampersand. That's a universal reference inside the code. And it's that we can use that in a lambda, but you can even have a universal reference like that as a reference in your code. And in fact, this lambda is a shortcut for a class that is defined for you, where the function call operator takes universal reference as a parameter. But we can also, and we might also need auto ampersand ampersand for other stuff. And here's a maybe pretty surprising example. So let's assume we just want to set all the values in this container to a certain value, yeah. So here, for example, we have a container of strings. So assign to all of them the value reset. Here you see how this works. We just, this is a value we only have to read. So set all takes this as a const t reference and an L value reference const. Let's iterate over this and and assign this. And we iterate over all the values in this vector. We modify them. So we have to iterate by a reference, and we can't declare this const because we modify each value in this vector gets this argument. Everything looks good. But let's use our container for Boolean values. And now let's set all the values in this container to true. And we got a compile time error. Think about, my goodness, what is that? Maybe you have seen that problem, maybe not. Not many people work with vector bool, but it does not compile. What the hell is going on here? Well, let's look what the range-based for loop, which we use here, does. The range-based for loop, or the code we have here, is roughly equivalent to this. So we have, we initialize an iterator with the begin of this vector. And while we are not at the end, we iterate over all the elements. And then we deal with each and every element this iterator points to. So star pos, so to where the iterator points. And now on the left-hand side, we have this expression. So we say we take the current value in our vector, and then we assign this to an L value reference, which is not const, because we modify it. However, there's a problem with vector bool. So if our container uses Boolean values, vector bool has internally has a wrapper around the bits, around the Boolean values in vectors. Vector of bools, the elements are just bits. So the objects are just objects that wrap a bit in a byte or in multiple bytes. They are objects. And that means what you get back here with star pos is a temporary object. It's a proxy object. And this temporary object is then assigned to a non-const L value reference, and that's simply not allowed. You can't assign temporary objects to non-const L value references. And if we try to use const here, then we have here the problem that we would make everything const. If we skip this ampersand, we could not modify the values. So what is the solution? The solution is, again, use a universal reference. The thing with 2 ampersand and no const, and for arbitrary types. So whether it's a template parameter or whether auto is used, doesn't matter. We have the same rules there. So now we have here an auto R value reference, and that's okay, because a universal reference, that's where the name comes from, universally binds to everything, to all objects of all value categories, to even to temporary objects. And that's the only type where we can bind to any object without losing the information whether an object is not const. It's the only type that can do that, or kind of type. And therefore, you sometimes need universal references not to forward something. We don't forward here anything at all. Do you see any forwarding? No, we just need a reference, and a reference that can refer to everything. And so this works. And that's why I'm not happy that we decided to give the name a forwarding reference as a name. This is a universal reference. And if you apply forward to it, you make it a forwarding reference. But here we just use it for a different purpose. And one good purpose of this reference is it can refer to everything and can keep the information whether something is const or not. We have no other way to do that in C++. Okay. There is... talking about setters, I come to the other questions at the end. Please excuse if that's okay. So there's another topic, talking about setters or some kind of setters. Let's talk about getters. And there's a flaw, or there's sometimes even a war between programmers about the question, should getters return by value or by reference, const reference ideally? So here's a good example. In our class, we have a vector of t, and the getter here returns by value all the vector of t. And that's safe, but slow. So if we do something like this, so I want to just know how many elements I have. So if this container doesn't have a size function, which it might have, but if you don't have that or need something else, then you would have, okay, get values, gives you back this by value. But returning this by value means that we create a copy of the whole vector of all its elements. So if it's a vector of 1 million strings, 1 million strings will be copied, including memory allocation, and the vector also needs what's 1 memory allocation for its internal memory. That's very expensive just to get the size. So the answer of that, which is often done in practice, is, oh, well, then a getter can return by reference. Because I call this for an object, it should still be there when I use this reference. Well, pass by reference is usually safe, because what you pass does exist until you leave the function. But returning by reference, there's some danger. And returning by const reference here can go wrong. My favorite example is an example where you don't see or even feel that there could be something going wrong. It's the range-based for loop. The range-based for loop has a significant problem. I would consider this as a bug, and I hope this will be fixed pretty soon, say for C++23. If we have a function returning a container of strings, so something like this, with elements being strings, and if we then call this and directly ask for the values inside and iterate over these values. So let's iterate over all values returned by a function that gives us back a container of strings. The best you get here is a coda, because then you see that you have a problem there. Because the range-based for loop, the way it is specified right now, has a significant problem with references to temporaries. If you have on the right side references to temporaries, and get values returns by reference. And the problem is that with the implement specification used inside, the temporary object is destroyed before we start with the loop internally. As I said, I still have the task and want to fix that. I think this is a major flaw because it is the most important loop we have. But we have to warn even beginners about using this loop for each and every case. And that should be fixed. I hope this will be fixed very soon. But we have to discuss that, because the problem is, to fix that, we have to extend the lifetime of this return value. And extending the lifetime of a return value might temporarily create more footprint in the program. So that's something we have to consider. And that's good that we have to consider that and that we do that. So that is the problem. And this problem will not occur if we return by value. So it seems we have to decide between cheap or safe. And there's a new way to do that now. And the new way is this. You can overload the getter for R-value references. So this is a way to qualify this getter that this will be called if the object I call this for is, as usual, for to ampersand, an R-value. So that means it is either a temporary object or an object qualified with move or marked with move. And const L-value reference, that works for everything, but that's the second best option. If this fits, that's better. So for all objects, it's like having a function taking a const L-value reference. For all other objects, we return by const reference. So that's good now, because now we have no problem here. We have a temporary object, and this getter returns by value. And here, we are cheap because we have an object with name, and we can here return by reference and ask for the size. Please also note that we have a move here. So when we have a temporary object and we ask for the values, we make the copying cheap, because by definition of move or of a temporary object, we no longer need the value of this object, so we can move out the whole vector of strings to the caller, and that makes this cheap again. So this is not only okay, this is also cheap if Move Semantic is supported for a data type. And that's a good thing. So I don't want to see anymore that you return by reference in getters. Don't do that. If you think that's useful, well, then do it in certain cases. So say in general, maybe I return by reference, but for when there can be lifetime problems, I return a temporary object. For a temporary object, I return by value. And by the way, we discussed right now that we even should qualify assignment operators and other operators that way to fix some flaws we could have when we use assignment operators in some interesting ways. So, and let me finally show you that if you have this support, then it's a good idea to mark your object with move if you call get values and you no longer need this object. That makes this call cheap. So you move out the object where you need no longer the vector of string. You move out these values as vector of strings to here. If you would not mark this with move, you have the problem that because this returns a const reference, that here we would copy things unless maybe optimizers, compilers can optimize that. So if you have never seen that, it can make sense for member function calls to mark objects with move. And by the way, I had recently an interesting discussion whether then this move should apply to this or to the whole thing. But if it's not a member function, but just a data member, so I haven't said everything about that. If it's a data member, then a lot of additional complicated rules apply. That's it. I mean, we have the hour is almost gone. So to have some time for some questions, let's see where we are. So I did definitely not show all the problems. We could, I could, if for more time, we could do some other stuff with this class and fall into a couple of other traps. But what we have seen here is const disables move semantics. So don't use it when you see something is used again. And that especially means don't return by const value. Don't do that if that's your style. Const R-value references are possible, but it's a semantic contradiction. To always adopt values you can take by value and move if move is cheap, etc. If you have 2 ampersand for function template parameter or with auto, you have a universal or forwarding references, and unless the T is not a local function template parameter or the argument is const, or T is an expression like this. And as you have seen, std string with 2 ampersand can be a universal reference, although it doesn't look like that in full function template specializations. Universal references do not always forward. That's why I prefer the term universal reference, because it's a little bit confusing that we name it forwarding reference. It's also confusing because L-value reference and R-value reference, the name, this term, comes from the fact where can they refer to? And now it makes sense. Universal references can refer universally to all class, but forwarding is suddenly what can we typically do with that, but not always we have to do that. And I think that creates a big confusion, and I'm really not happy that we made this and introduced this term, beside the fact that we had an established term that was really working well. Yeah, maybe here, because I'm pretty sure we will discuss that at Twitter or somewhere else. Here's another example for a universal reference that does not forward. Let's take some arbitrary container type, arbitrary value type, arbitrary type and arbitrary value category. And let's iterate over the elements by calling cbegin and c.end. Where do you want to place forward here? And you are not really forwarding, we are calling for the C begin and end. And depending on the container here, we might, if it's const, get a const iterator. If it's not const, we get an iterator. That might be important because you have overloaded iterate for taking const iterators and non-const iterators. So that's another example for a universal reference that does not always forward. Getters should return by value or should be overloaded on reference qualifiers, and use auto ref, so a universal reference in a generic range-based for loop to support even containers where the iterator is a temporary object, refers to a temporary object. The range-based for loop is broken currently when iterating over references to temporaries, and it makes or can make sense to use move for member functions. That's it. So, time for some questions, maybe. And maybe before I take the questions, let me say something. I learned a lot over the past half year because since winter of this year, I wrote just a book about move semantics. So there, I learned a lot I didn't know before. Even I'm standardizing C++ for 20 years, but I'm not the smartest guy. I only document what we standardize. And this is done now. It's done. It's out. It's out as an ebook and as a paperback at Amazon. It has 250 pages. So, well, you might see these slides, but a few slides are missing. or read the book. And here's a website where you can find more information. I hope you enjoy it. Please give me feedback. And then I'm fine to take questions. So let's see what I have here. When specializing a function template to take a string double ampersand, I told you, I said that it's a universal reference. Is there any way to specialize it or to take only an R value reference? Yes, there is. What you usually can do, since C++20, you use a requires clause. What you simply say, you can ask for the template parameter T, whether it's an R value reference or whether it's an L value reference. Well, in fact, if it's an L value reference, then it was an L value passed, and otherwise it's not a reference at all. Sorry, I was not quite correct here. So, but you can check that. There's a special rule for if you use universal references, then the objects, the parameter type T is when an L value is passed, it's an L value reference. Otherwise, it's just a plain type T, so plain type string. By testing this and requires or enable if, it's possible to do that, and it's described in the book. Haha, good question. Next question. Not sure I can read the next question. STD forward val or static cast decal type val R value reference val. That was for a specific slide, I think. If you send me again which slide you mean, I'm happy to answer that question. In general, forward is a conditional static cast. So or conditional move by having a special static cast. I can't answer this question now immediately without seeing the slide you mean. And yes, it might be that I had. No, I have to, no answer. I can't answer that now. Sorry. Next question. Are there possibilities to statically, there's always a name in front of that. Show click to view more. Mia, can you remove the top question so that I can see the next question? Thank you. Are there possibilities to statically assert if a type is forwarding reference to implement things like it? Yes, as I said, you can do that. Statically assert. Is it statically assert? Yes, you can do that. It's known at compile time. So as I told you, when an L value is passed, what you get as a parameter type T is an L value reference. You can check this with enable if. You can also static cast that. And you can also use if const expert. Sometimes you need if const expert to decide on whether an L value was passed or whether an R value was passed. You can also do that. What is the difference between saying that a member function is const ref and const? Well, I assume we mean the return value. The return type, if it's const string, you return by value, but for the caller, you say it's not allowed to modify it. If you return const L value reference, you don't create a copy. You have really to make sure that what you return is something that is still living. So like a member with some flaws, we have seen that, or maybe a static object also. So that there is a huge difference. And pretty often, if you return by reference, be very careful. Normally, return values should only be by value, and maybe with some exceptions, if you exactly know what you do. Could you use auto R value reference instead of having to add template onto a member function? Could you use auto? And that was slide 17. Thanks for the slide. That helps me. So could you use auto instead of having to add template onto method. Yes, you can since C++20. Yeah, in C++20, we have the feature that we can here specify auto. Auto R-value references were allowed before C++20 only for lambdas, and now it is there also everywhere allowed. And it's a shortcut for just being a template parameter. But then you need here Deckel type of V instead of U, of course. Okay, maybe 2 or 3 other questions. Are there any differences between Deckel type auto foo equals F, auto reference foo equals F? Oh, yes. Oh my goodness, I didn't talk about Deckel type auto. Deckel type auto is a nightmare. Deckel type auto is using very interesting rules of Deckel type to decide how we should return a value, but with which type. And there's a special rule with Deckel type. If you pass a name, it gives you back the type. If you pass an expression, Deckel type gives you back the value category. So Deckel type auto is something that in many cases works well. But for example, you can get in big trouble if you then in your return statement return a name and have parentheses around it. Don't do that, because then you return the object with an L value reference, because with the parentheses, Deckel type asks for what is the value category of the object and might give you a different result. In general, the difference between Deckel type auto and auto with 2 ampersand is auto with 2 ampersand is always a reference. Deckel type auto is sometimes a value and sometimes a reference. And we need that in return type. So if we want to perfectly return something in a function, you need Deckel type auto, which you then might even have to qualify as return type in a lambda, because by default, there the return type is auto. All explained in the book. Haha, it works good as advertisement again. Can't the standard repair the bug to extend the lifetime? Yes, we can. Well, it's not the standard that repairs it. It's the people who decide what is in the standard. So the committee, I'm still upset that we have this bug, and I'm still hope we can fix that. As I said, it's not that easy. Because we might create in some places more temporarily more memory footprint, and that can sometimes be a problem. I don't see why this is a problem here in this case. So I would not fix it in general for references to extend lifetimes for everything. But in the range-based for loop, I would definitely like to hide the problems, because nobody sees that internally references are used, which even in separated statements, so that lifetimes end in the middle of the range-based for loop. That's a nightmare. How many things are nightmares? Everything in C++ is a nightmare, of course. That's easy. Well, it's a very successful nightmare. Don't get me wrong. We have a problem with the complexity of this language, and there's a good reason for that. And there's a history for that. We have 50 years of backward compatibility, because 50 years ago, C was invented, and we struggle with a couple of things we definitely would do now better. And of course, we learn, and of course, we make mistakes. It's like every other software project. The problem is we have to be backward compatible. So if you don't like things and want us to make it better, join the committee. We need people who help us to do things right. Thank you. Okay, last question. Would you suggest to use void f const string r-value reference equals delete to avoid unintentional copy? Oh, equals delete is definitely something to avoid unintentional copies. I think I need for this answer a little bit more context. So that's it. I hope I could answer a few questions. Feel free to send me emails or whatsoever, or you can feedback, and if you like, tweet about this talk. I learned a lot. I might still learn, and I do still learn. I know that. And let's all help to make this language better. And so that it's especially easy to use in the general case for the ordinary programmer. Thank you very much. Have a good day, and vote. Don't forget to vote. It's important this year. Thank you.